Hello, this is my YouTube channel, The Physics Channel, and today we are going to solve a past paper that is from 2020. June course code is 5054 and it is variant 1, paper 2 theory and variant 1. General instructions in section A, you have to attempt all questions. In section B, you have to attempt any two questions. But this section of instructions, I am trying to solve all the questions. These are general instructions. You may go through it. This paper is of 75 marks. And the number of marks for each question or part question is shown in square brackets. So let's start the paper. Section A. Answer all the questions in this section. Answer in the spaces provided. Question number 1. Figure 1.1 shows the thinking distance and the braking distance of the car being driven along a dry road and along a wet road at the same speed. So on the dry road, the thinking distance is 18 meter and braking distance is 43 meter. On the wet road, thinking distance is same 18 meter and the braking distance is 60 meter. What we are asked to do is calculate the total distance for the car on the wet road. Total stopping distance. So we know that stopping distance is equal to thinking distance, that is 18 meter, plus braking distance, that is 60 meter. So 18 plus 60 is 78 meters. So our answer is 78. Now complete the sentence. Thinking distance is the distance that is traveled between seeing a hazard and. What is the thinking distance when a driver sees a hazard or an obstacle and he start applying brakes? So the distance covered during this moment, during seeing hazard or obstacle and applying brakes, is called the thinking distance. So we will complete this sentence as the thinking distance is the distance traveled between seeing a hazard and application of brake. Application of brakes, or you may write it start application of brakes. Suggest why the thinking distance is same on both roads. So if you read out the question carefully, you will get its answer in the question. It comprises of 1 mark and you see that the car is being driven along a dry road and a wet road at the same speed. So there are two possibilities why the thinking distance is same on both the roads. One possibility is already given in the question. You may say that the car is driven at the same speed, on both the roads, dry and wet roads. And other possibility is that the car may be driven, both cars may be driven by the same driver, by the same person. The cars may be driven by same person on both the roads. Both the roads. Part C, part number 2. Explain why the braking distance is larger when the road is wet. So we know that wet road provides less force of friction between between vehicles, wheels, and road. So the car or vehicle decelerates slowly on wet road is compared to dry road. Hence, it covers more distance. Now, let's move towards question number 2. Question number 2 says that the student performs an experiment to mark the center of mass on a thin piece of card. There are two holes in the card. Figure 2.1 shows the card and two lines that the student draws on the card. The figure is given. The white portion or the white marks represent the hole, while the lines drawn intersect at C, which is the center of mass. But we are asked to describe a method used to draw these two lines in their correct position on the card. Make clear what extra apparatus is needed. You may draw a diagram if you wish. So it is a simple question. It is mostly related to practical, alternate to practical, but let's solve it here. First of all, let's have a look what apparatus we will need. So the apparatus we will need is we will need a clamp, a stand, we may need we will need a needle or pen, needle/pen, and 4 is plumb line. So it is a stand. This is the clamp. This is the needle. Let me label it needle or pen /pen. This is the clamp. This is the stand. What we will be doing, we will try to span this card through the given holes. Let's say it is hole A, it is hole B. Let's suppose I suspend this card from hole A. So let's say this is the position of the card. Sorry for rough drawing. I'm not expert in drawing, but let me make it a bit easier, a bit simpler. Or you may just imagine we will be suspending this whole card from this point A, and we will leave it until it gets stationary and draw a vertical line using plumb line. And the same we will repeat it for B hole, and we will draw a line and it will intersect at C. So the proper answer will be we will use a plumb line, a stand, needle or pen, and clamp. Now we will write the procedure what we actually are doing. Plan to determine the center of mass, C bar. Now the procedure will be as follows: suspend the card from hole A as shown. Along the pin. And wait till it gets stationary. Mark a line using plumb line. Repeat the same procedure for hole B. So this is the first part of this question. We will get, you may write, we will get this cm or center of mass for the card. Now let's move it further. In part B, the student holds the card loosely between her fingers. The card is vertical, resting with its lower edge on the bench as shown in figure 2.2. The card is slightly tilted as shown in figure 2.3 and then release. When theta is small, the card falls clockwise back to the position as shown in figure 2.2. Explain why the card falls anti-clockwise when theta is large. So, in the same manner, we will have a look towards the center of mass. If you see in the figure, it is slightly tilted. The theta is small, so you may see that still its center of mass is falling between point A and B, line A and B, which is the base of the card. So when it is released, it will fall down and it will gain back its initial position as it was placed. But it will move anti-clockwise when theta is large. So why is it when theta is large, the center of mass of the card will fall out of the baseline, baseline that is marked AB. So the card will fall anti-clockwise. Part 2 state one change to the card that makes it more stable. So for stability, we know that we can get higher stability by lowering its center of mass. So by lowering the center of mass of the card and another change is also possible, which is that increasing its baseline, or only you may write its base AB. The card will be more stable. So this is all about question number 2. Question number 3. A student suspend a spring from a support. He attached different loads to the lower end of the spring. For each load attached, he measured the extension of the spring. Figure 3.1 shows the extension load graph obtained. Like this is the graph the student obtained from performing the experiment for different loads. We may have a look on the graph. Extension is taken along y-axis. Let's say the extension is being represented by x, that is the change in the length of the spring due to the load that is represented in Newton, so it means F. And you may see that the graph is a straight line. What we are asked The extension of the spring is directly proportional to the load. It is quite obvious from the graph as it is a straight line. So extension of the spring is directly proportional to F. Let's write it. X is directly proportional to F. So we may write X equals to KF. For our easiness, let's write it. Now we are asked state the two features of the graph that shows this. So the feature of the graph is that the graph is a straight line, and as the graph is straight, so it have a constant slope. So we will write the graph is straight line having constant slope. Another feature is that the line, you may see that it's passing from the origin. The line is passing through the origin. And at origin we will write 0, 0. In the next part, describe how the student can show that the spring reaches its limit of proportionality at 8 Newton. So let's have a look on the graph. As we know that from 0 to this point, I will mark it as from O to A. We have a constant slope. Let's say that let's us find out the slope, that is y by x. Y is 6 and x is 8. So 3 by 4 is our slope. So how a student will show that the spring has reached its limit of proportionality at 8 Newton? So for this we will do a simple change in this whole setup. We will add some more load. Let's say it is increased del y, and at y-axis it is del x. So what we will do, by increasing the load beyond 8 Newton, and measuring the extension let's say y centimeter. After that, calculate the slope. Is shown in the graph. That will be, for example, change in y by change in x. This formula will be used for finding out the slope. So, after finding out the slope, if the value, as we have find out the slope earlier for the graph that was 3 by 4, So after increasing the load and then finding out the slope, so if the value of the slope is not equal, if the value of the slope is not equal to 3 by 4, that was the slope of the graph. We have find out, here it is. So if the value is not equal to 3 by 4 after the addition of extra load, we may say that the spring has reached its limit of proportionality. This spring has reached its limit of proportionality. You may add that and write, or you may write that 3 by 4, that was the slope of the graph, that was constant. So if we increase the load and the slope does not remain constant, means it does not get the same value 3 by 4, so it means that the spring has reached its limit of proportionality. In part C, a spring is used in a simple device known as accelerometer, shown in figure 3.2. A load, a mass that is attached with a spring. The mass is 5 kg and it is a smooth surface. The spring is fixed at one end and at the other end is attached to the mass of 5 kg. The mass rests on a smooth horizontal surface. There is no friction between the mass and the surface. Acceleration is towards the right side. The whole device is placed in the car. The car accelerates and the student notices the extension of the spring is 3 centimeter. Using figure 3.1, figure 3.1 is the graph. We have to calculate the acceleration of the car. The main thing is in the figure 3.1 is the slope, that or you may say that the relationship between extension and force, that is x directly proportional to f, x equals to kf and k equals to x by f. This is the whole equation for the k, which is the constant for the spring. Here we have mass of 5 kg, so we write mass equals to 5 kg. The extension in the spring is 3 centimeters, so x equals to 3 centimeter. Using figure 3.1, we will calculate the acceleration for the car. For acceleration, let's use the equation we derived for the k, which was equal to x by f. X was 6 and force was added, it gives us 3 by 4. So the value of k is 3 by 4. Now using this value of k, we will find out the force for this setup, for the mass attached to the spring. Again we will write it as F equals to x by k. Here x is 3 centimeter, so we will write the value of x, and k is 3 by 4. So it will give us 3 cross 4 multiply 3 multiply 4 divided by 3, 3 will cancel out with 3 and we will get 4 Newton. So force equals to 4 Newton. Now we need to find out the acceleration. For acceleration we will be using Newton's second law of motion, that is F equals to ma, a equals to F by m. F is 4 Newton, we just find it out, and the mass is 5. So 4 over 5 is 0.8 meter per second square. So the acceleration is 0.8 meter per second square. Now let's move to question number 4. Glass and iron are both conductors of heat. However, glass is good conductor of heat and iron is good conductor of heat. This part A. Describe using ideas about particles how the conduction of heat takes place in glass and in iron. You should make it clear why iron is a better conductor of heat. So we know that by heating a substance, the kinetic energy of molecules or particles or atoms increases, which results in the vibration of the particles more vigorously, more roughly, more randomly, and it results in the transfer of heat or the transfer of energy to the nearby atoms, to the nearby particles, and transfer of heat takes place from hot body to cold body. While the same thing happens in iron, but in iron we have also free electrons. So let's write it down by heating particles or atoms of glass, they start we can say that the kinetic or their kinetic, we may say that of atoms of the glass, their kinetic energy increases and they vibrate more vigorously. This results in the transfer of energy slash heat, energy or heat from hot hand to cold hand. And what happens in iron? The same thing happens in iron, but in iron we have atoms along with free electrons. So here we will write that by heating iron, the Ke of atoms and free electrons increases. The atoms start moving more vigorously. And the collision between free electrons with the particle increases. This results in much faster transfer of heat from cold, from hot and cold, and from hot and to cold hand. So the only difference between the transfer of heat in glass and iron is that in iron we have free electrons. So the transfer take place because of atoms and free electrons in iron. But in glass we do not have any free electrons, so the transfer of heat take place by the vibration of atoms because their kinetic energy increases and it start vibrate more vigorously and passing on their kinetic energy to the neighboring particles, which result in the transfer of energy. So the slight difference is that in iron, particles or atoms along with free electrons are responsible for the conduction of heat, while in glass only the particles or the atoms are responsible for transfer of energy. In part B, question number 4, part B shows the apparatus used to show expansion. Here we have a glass tube through which we have measured the liquid level. The liquid is placed in a glass flask and water is the liquid and heat is given. The glass flask full of water is heated. A student is surprised when the liquid level X in the glass tube falls for a few seconds before it rises. What we are asked suggest why the liquid level falls and why it then rises. So why it falls? Because when we start heating first of all the expansion in the glass flask will occur, resulting in lowering the liquid level. Then expansion in the liquid will take place. Liquid will take place rising up the level. First of all, when we start giving heat to the glass flask will expand, and as a result, the level of the liquid will falls down. And after that, heat will be given. The heat will be transferred to the water inside the flask, and it will result in the expansion of liquid and results in rising up the level. Part number two. Describe how heat is transferred throughout the water in the flask. When heat is given to the water at the bottom, it like when the water at the bottom of the flask is heated, it becomes less dense and it rises up. The cold water in the surrounding cold water, which is less dense, which is more denser. Cold water is more denser. Water denser. Takes its place this process starts convection current. Current and heat is transferred through out the flask through these convection currents. Convection currents. Now, question number 5a part. Use the relationship between pressure, force, and area to explain why it is harder to cut something with a blunt knife than with a sharp. So we know that P equals to F over A. P is the pressure, F is the force, A is area. Thus, a blunt knife has more area, so less pressure is
whereas the sharp knife has smaller area, so large pressure is generated. Question part B. Experimental measurement on gauge pressure were made by Robert Wiles. He showed that P1 equals to P2 where P1 and P2 are the initial and final pressure of a gas, and V2 are the initial and final volumes of a gas. What we are asked, state two quantities that must remain constant when this equation is used. So the two quantities, one is the temperature should be kept constant. Temperature should be kept constant. The other thing is mass, or we may say number of particles. Should be constant. Should be constant.